In today's lecture, we will look at how enzymes catalyze reactions, what are the various mechanisms by which this catalysis occurs. Okay, as we looked at last time, a major part of the enzyme catalysis is in binding. Once the enzyme binds the substrate, then there must be a reaction that occurs in the active site, and once the reaction occurs, there is a dissociation to give you the products. And here somewhere along this line, there has to be a transition state that is involved in the uncatalyzed reaction. And now in this transition state, since there is an acceleration of the reaction, the newer transition state that is being generated must be of lower energy. So with this general picture, let us look at the various mechanisms by which enzymes can catalyze reactions. So before that, so let us look at a general picture of transition states. So imagine a reaction A goes to B. Okay. A typical energy profile will look in the following manner. You have a starting material, you have a product, and there is a barrier that the starting material has to cross to get across to the product. And this barrier is represented by activation energy or by delta G double dagger. Okay. Although these two terminologies are not necessarily interchangeable, but for the purpose of this course, we will use them in an interchangeable manner. So intuitively, what we can determine from, or experimentally what we can determine from a reaction is actually the rate of a reaction. So from the rate, we can deduce what is the activation energy. Okay. We will not go into those details at this point. However, suffice to say that when the transition state is stabilized, it would result in acceleration of the reaction. So what it means is that if the barrier required is actually significantly lower when compared to the parent reaction, then the reaction rate would go up. So if you take let us say a series of reactions of substrates which are related structurally, the assumption one could make is that the ground state energy of these reactants do not change a whole lot, neither does the ground state of the products. However, when the transition state is stabilized, you will see an acceleration in the rate. Okay. So the rate of the reaction is dictated to some extent by the stability that can be imparted to a transition state. On the contrary, you could also have a situation where the transition state is not perturbed a whole lot. So this energy difference is not a whole lot, but if the ground state energy goes up, okay, then you would still have the same result of acceleration in reaction. In reality, in enzyme catalysis, it is a combination of these two factors, that is, the ground state energy can also go up and the transition state energy can also go down. The combination of these two factors results in catalysis. So with this background, let us look at some mechanisms of enzyme catalysis. So there are several broad ways in which one understands enzyme catalysis. So we will look at some of these cases in detail over the period of this lecture and the next lecture. So the first one is approximation. So here what we will understand is that when you bring the reactants close to each other, then it can result in a dramatic increase in the rate of a reaction. The second concept is covalent catalysis. Here you change the outcome of or you accelerate the reaction by changing the intermediate that is involved during the reaction course. And then we will also look at general acid base catalysis and how transfer of a proton or a hydronium or a hydroxide ion in an appropriate manner can result in catalysis. And we will also look at electrostatic catalysis, desolvation which results in increased rate, and also strain and distortion. Together these effects result in, as I mentioned earlier, it results in the stabilization of the transition state or destabilization of the ground state and result in acceleration of the rate of the reaction. Okay, now let us look at approximation. Approximation is as I mentioned earlier, is a rate enhancement by proximity. Okay. So for a reaction to occur, let us say A and B, they need to collide, and this collision occurs when they are in close proximity and they give out the products, let us say C and D. Okay. But in reality or in an enzyme, the enzyme can bind the substrates or in a particular case a single substrate in a manner such that it can bring one of the reactants and the other reactant close to each other, and because they are brought close to each other, the degrees of freedom that are required to be overcome to reach a favorable transition state is lower. Okay. So, of course, there is a loss of rotational and translation entropy in this process, and but this entropy loss is offset by favorable binding energy. Okay. So, here the binding of the substrate, which is the first step in enzyme catalysis, provides the driving force for catalysis. Okay. Now, in order to understand this, let us take an example of a reaction of acetate with acetyl ester, okay, aryl acetate. Okay. So, now here in this case the acetate attacks the aryl ester and kicks out aryl oxide ion, which kicks out aryl oxide ion. Okay. So, this reaction, as you can imagine, would be a second order reaction, and if you measure the rate constant at 30 degrees, you get a value of 3.36 times 10 power minus 7 per molar per second. Okay. So, in order to understand how approximation helps, let us study this reaction within an intramolecular manner. Okay. So, what we are doing here is we are conducting the same experiment, but with an reaction with an intramolecular reaction. So, here you have the starting materials are located in the same molecule. This type of mechanism can operate and give out aryl oxide. Okay. If we measure the rate of this reaction and derive a rate constant, we would get a first order rate constant, because this is dependent only on the starting material in this case, and the value of this is 7.39 times 10 power minus 5. And similarly, when we carry out this reaction over multiple substrates, we find that the rates of the reactions are in these values. Okay. But in order for us to understand approximation, we cannot compare a first order rate constant and a second order rate constant. So, we need to figure out some way in which we can actually compare these two values. And so, in order to do that, what we do is we define a term known as effective molarity. Okay. Effective molarity is nothing but the concentration of a reactant required to cause the intramolecular reaction to proceed at the same rate as the intramolecular reaction. Okay. So, if you set the second order rate constant to be 1 per molar per second, that is for this intermolecular reaction, if we set the second order rate constant to be 1 per molar per second, and then what we do is we divide the first order reaction that we are interested in, which is the intramolecular reaction, and the rate constant of that is divided by the rate constant of the second order reaction. So, that is what we define as effective molarity. Okay. So, if I do this division, then I get a value of 220 molar. Okay. Now, what is the meaning of this 220 molar? What it means is that this is the concentration of acetate that is required in an intermolecular reaction, where the rate of the reaction can match the intramolecular reaction. Okay. So, it means that you need a very extremely high concentration of acetate for this reaction to proceed at the same rate as the intramolecular reaction. Okay. To put this in perspective, if you take water, pure water, the concentration of water in pure water is 55 molar. So, it is impossible to reach this high concentration of 220 molar of acetate. Okay. So, therefore, what this effective molarity is a very useful term for us to understand the effect of bringing together the two reactants in the same molecule. So, it appears that holding these groups proximal to one another, particularly in the case of when the orbitals are in a favorable overlap condition, that the enzyme substrate complex aligns it in such a manner that the reaction goes in a very rapid manner, and it becomes an important contributor to catalysis. I will repeat, holding these groups proximal to one another especially in an enzyme substrate complex, the reacting groups are aligned in such a manner that favorable interactions occur and it results in a very great acceleration in the rate of the reaction. Okay. And these types of intramolecular reactions can go up to 10 power 16 molar, effective molarity can be 10 power 16 molar. So, that is a tremendous increase in the rate of the reaction when compared to an intermolecular reaction. Okay. So, one of the ways in which enzymes catalyze or accelerate reactions is by bringing together two starting materials and enabling the appropriate conformation to be reached, so that the reaction goes faster. Now, let us move on to the second topic, which is covalent catalysis. So, as we have looked at, there are a number of naturally occurring amino acids and there are few amino acids which have nucleophilic groups such as a thiol or alcohol. Okay. So, these nucleophilic groups can participate in nucleophilic substitution reactions or nucleophilic addition reactions, and these can enable acceleration in rate of a reaction. Okay. So, this concept is known as nucleophilic catalysis, and it is a subset of covalent catalysis which involves the formation of a covalent bond. Okay. In order to understand this better, let us look at an example of a reaction of this thioether. So, in organic chemistry, we are all familiar with the concept of neighboring group participation, also known as ankymeric assistance. So, what happens in neighboring group participation is that a neighboring group carries out, or a neighboring group facilitates the reaction by changing the pathway which is taken or for a reaction to occur and a product to be formed. Okay. So, here you can imagine that reaction of an alkoxide with this alkyl chloride, which is normally an extremely slow reaction, is dramatically accelerated when you have a neighboring group participation. So, here this lone pair on the thioether can move in here, kick out a chloride and produce a highly reactive episulfonium ion intermediate, which then is opened up by the alkoxide to give you the product. So, when this type of catalysis occurs, what in essence happens is that the path of the reaction is actually changed, okay, and this results in acceleration. So, one of the amino acids that can be involved in this type of an covalent catalysis is methionine. As you can see, methionine has a thioether functionality, and once it attacks, in this case it reacts with a substrate, it produces an intermediate which is highly reactive, and that covalent adduct can now be opened up by, let us say, an alkoxide or water to give you the final product. Okay. So, in this case we can look at the formation of an amide bond. Here you have X minus, which can be cysteine or serine, reacting with an amide to form, this is a generic reaction of a carboxylate group. So, here the X minus attacks the C double bond O, produces a tetrahedral intermediate, and now this tetrahedral intermediate is actually activated and then subsequently attacked by a nucleophile can give you back the reactant and give you a different product. So, this can, for example, be a trans esterification reaction or even amide formation or amide hydrolysis type of reaction can occur through this type of mechanism. Okay. So, covalent catalysis is very important mechanism by which enzymes can accelerate a reaction. The third major way in which catalysis can occur is through acid base catalysis. As we all know, amino acids have both acids in the form of a carboxylic acid as well as a base in the form of amines. Okay. And in the broad terminology, we have Lewis acids as well as Bronsted acids, but suffice to say, anything that can donate a proton is considered an acid, and anything that can donate a lone pair is considered a base. So, with that definition, we can look at acid base catalysis, and there are generally speaking, there are two forms of acid base catalysis. one is called a general acid base catalysis, and the other one is called a specific acid base catalysis. Okay. So, let us look at the hydrolysis of ethyl acetate as an example. So, ethyl acetate, if you put it in water, water is being a nucleophile, can attack and produce acetic acid and ethanol. Okay. Now, in the case of the first example that we look at is specific acid base catalysis. Here, if the catalysis occurs by hydronium ion or by hydroxide, then the rate of a reaction is determined only by the pH and not by the buffer concentration, and therefore, any form of catalysis by hydronium or hydroxide, but not the buffer concentration, is referred to as specific acid or specific base catalysis respectively. So, let us look at the example of hydrolysis of ethyl acetate. So, this is extremely slow reaction, and what happens is that water attacks here and generates a tetrahedral intermediate, and then the tetrahedral intermediate collapses and kicks out ethoxide ion, which can in turn pick up a proton from acetic acid and give you ethanol. Okay. So, this reaction is very slow, right, but one could think of accelerating this reaction by one can think of increasing the rate of the reaction by increasing the reactivity of either the nucleophile or the electrophile. So, this can be achieved by converting water to hydroxide. So, hydroxide is a better nucleophile when compared to water, and therefore, just increasing the pH of the reaction can increase the rate of the reaction. So, what we have done here is converted water, the previous nucleophile, to hydroxide, and now hydroxide can come and attack, form the same tetrahedral intermediate and kick out ethoxide, and then subsequently it equilibrates to form acetate and ethanol. Okay. So, indeed, when we carry out hydrolysis of ethyl acetate in basic pH, we do find very high rates of reactions. Similarly, when you lower the pH, that is increase the concentration of hydronium ion, you also find an increase in the rate. Okay. And the way we understand this is that when you have hydronium ion, the lone pair on the carbonyl can react with H3O plus and form a protonated carbonyl intermediate, which of course exists in this resonance form. But now, because you are generating this very highly reactive protonated carbonyl intermediate, the attack of the nucleophile, in which case it is water, happens much faster, and now the reaction rate actually ends up going up. Okay. So, therefore, acid base catalysis here is a concept where we would increase the reactivity of the nucleophile or increase the reactivity of the electrophile by simple protonation or deprotonation reaction. Okay. Now, so therefore, in principle, if I add both acid and base into a reaction medium, I should be able to increase the rate, correct. However, in reality that does not occur, because what happens is that acid base reactions are very fast, and therefore, you will have neutralization and you will lose all any potential for catalysis. Now, in the context of an enzyme, the situation is very different. Okay. So, in the enzyme, since we looked at how the protein folds up and there are certain residues which are present in spatially in a particular area, those can facilitate protonation or deprotonation, which results in acceleration of rate of reaction. So, here is an example of a relay type of mechanism, where this base here can donate a proton to water, which will generate hydroxide ion, which can then attack a carbonyl, and which in turn can pick up a proton from another base from another acid and produce the base. Okay. So, here is an example of, or a hypothetical example of, a relay mechanism, and since enzymes have very hydrophobic cavities and there are residues there which can be in both protonated as well as deprotonated forms, this type of mechanism is possible. Okay. We need to understand here that we all are familiar with the concept of pKa, which is a measure of how strong a particular acid is, but we need to appreciate that pKa measurements are typically are always carried out in water, okay, and once we change the medium, the pKa of a particular group can change. So, the way we understand is pKa is that the pKa would be lower, that means it will be a better acid if the conjugate base can be stabilized better. Okay. However, in an acid in an enzyme, maybe in a hydrophobic cavity, the conjugate base can be stabilized in a different way, even more perhaps sometimes, which can result in a better acid, or it can be destabilized, making the better acid actually a worse acid. So, these are a little difficult to understand conceptually. However, it has been established that pK values of amino acids vary quite a bit in proteins. So, this is something that we need to be sensitive about. Okay. Within the active site, therefore, it is possible that you can have a weaker base picking out a proton from a stronger base, or vice versa. Okay. So, therefore, it is not unreasonable to expect that certain reactions will occur which would never happen in solution chemistry. So, that is one of the interesting and important things about enzymes. The second form of catalysis is general acid base catalysis. So, here we define general acid catalysis occurs when acids other than hydronium ion accelerate the reaction rate. Okay. And similarly, general base catalysis occurs when bases other than hydroxide accelerate the rate. Okay. So, inside an enzyme, for example, the amount of free water that is present is generally very low, and therefore, you would have other sources of acid and base which can do the protonation and deprotonation. Now, how does one understand, or how does one distinguish general acid base catalysis from specific acid base catalysis? So, we looked at previously specific acid base catalysis. If I increase the pH, the rate of the reaction goes up, and if I decrease the pH, the rate of the reaction goes up. Okay. So, therefore, in specific acid base catalysis, the reaction rate is dictated exclusively by the pH of the medium. In general acid base catalysis, even if the pH is the same, but if you increase the buffer concentration and if you observe that the rate of the reaction goes up, then we would conclude that general acid base catalysis is operational. Okay. So, at constant pH as well as ionic strength, if you have an acceleration in the rate, right, just by increasing the buffer concentration, you have acid base catalysis. Enzyme mediated catalysis are general acid base catalysis reactions. Okay. And here, as I mentioned earlier, acidic or basic residue at the active site is used to facilitate the proton transfer. If you recall, we were looking at the relay mechanism, where a base can transfer a proton to the other end of the active site by just a relay mechanism. Okay. So, let us look at an example of chymotrypsin. So, chymotrypsin is a enzyme that cleaves peptide residues. Okay. So, here this aspartate over here, which is in a deprotonated state, can pick up a proton from histidine, and histidine is one of the functional groups which can act as a acid as well as a base depending on the context. Okay. So, when here it is, you can imagine that the carboxylate picks up a proton from histidine, and this proton in turn, and this histidine in turn can pick up a proton from serine, and now the serine residue is actually, the alcohol in a serine is actually made alkoxide, which is an extremely good nucleophile, and that attacks an amide and hydrolyzes it. So, this charge relay mechanism has been really well worked out, and you have what is known as a catalytic triad which does this, takes care of this catalysis. Okay. So, the catalytic triad is nothing but aspartate, carboxylate, histidine, and which has an imidazole group, and serine. Okay. But if you look here, the aspartate carboxylic acid, the pKa is 3.9 in solution, which is going to remove a proton from histidine, imidazole, whose pKa is 6.1, which in turn removes a proton from hydroxyl group of serine, whose pKa is 14. So, any well respected any good organic chemist would never agree with this kind of a reaction, this kind of a mechanism that is operational in solution. However, it can occur in an enzyme. Okay. One of the explanations is what we alluded to earlier, was that inside an enzyme or inside a protein, the pKa values of these acids and bases can be vastly different. The second explanation is that it is likely that a full protonation or deprotonation does not occur. So, you can imagine that this lone pair of electrons from serine is attacking here, and this serine residue is not completely deprotonated, whereas it is partially deprotonated, whereas the aspartate over here is pulling the electrons from histidine, and there as well it is not completely deprotonated or protonated in that case. And so, in this realm one can imagine that there is a differential distribution of charge density which helps or facilitates the reaction. So, here a combination of approximation of the groups, which is present, which is basically bringing these groups in proximity to one another, which is impossible in solution, occurs, which can change the which has a tremendous impact on the rates of reactions. To complete this reaction mechanism, serine attacks an amide, and this proton of serine is then picked up by histidine, and since histidine is a good acid base catalyst, histidine is a very good imidazole is a very good acid base catalyst. It can in turn donate a proton to aspartate, or it can form a weak interaction with aspartate, and now water attacks this which is now an ester. The water attacks this ester, forming the tetrahedral intermediate, which then subsequently undergoes decomposition to produce a free carboxylic acid. So, the mechanism, the reaction basically is the conversion of an amide to a carboxylic acid, and it is catalyzed by these three residues. And now, as you can see, these three residues are recharged to carry out this reaction once again. Okay. So, hydrolysis of an amide bond is extremely difficult to carry out in solution, and you need a number of reagents to do that, but in the presence of this enzyme such as chymotrypsin, one can carry this out with relative ease.